Okay, so I'd like to discuss this a bit for a number of reasons. Most of you folks are just starting graduate school. I'm going to guess that in the next 3 to 5 years you're going to read 1,000 to 2,000 papers. And I don't mean literally read 1,000 to 2,000 papers, but you're going to have to look at least that many papers and decide whether or not you want to read them. And hopefully the papers you're going to be spending the most time with are really important classic papers. So let's talk about that issue. What do you think goes for making a paper a classic paper? What are its attributes?
When they're cited many times.
I think that's a quantitative way to do it, but why? Let me change the question. What makes a paper get a lot of citations? And they're not necessarily the same reasons as a classic, but there's going to be a lot of overlap.
It's old.
It's old. So that means that none of you are ever going to write a classic paper during your lifetimes. Actually, most of the classic papers I've given you, not everybody, but the preponderance of the people who wrote those papers are still alive. Now, that doesn't mean they're young. Certainly being old does not make me a classic paper, because there's a lot of garbage in the literature, and it's old.
Sometimes those papers that we use are known standards that we compare against, so that most scientists will use that one paper as a known standard and they compete against it.
But I think you're answering my question with the question, and that is that it's a really, really good paper, so people use it. What makes for a paper to be of that nature?
The author primarily who wrote it, like for example, like Giddings is very, very well known, very well established.
Yeah, but that doesn't mean that every paper Giddings ever wrote was a classic, and that ain't true. He's written quite a few good, really classic papers, but just because his name is on it doesn't make it a classic.
It's the first time that some phenomenon has been explained.
I think that is an attribute of some classic papers. Let me get my writing pen here. First, of its kind / topic.
Uses several different approaches to verify.
Say again?
Uses several different approaches to verify the technique works.
How can I write that? Well documented.
The technique of chromatography can be applied to many areas.
General. It is widely applicable.
Yeah.
Going off of that, it should be useful.
Dare I write well written? think most classic papers do tend to be well-written, although again, I wouldn't say that that is an absolute characteristic. And certainly there are a lot of well-written papers that aren't very good. There's a real important characteristic of a classic that we haven't even gotten close to yet. I would say that the thoroughness of the treatment, or perhaps, who said it used more than one approach? But it could be a theoretical paper, and it could really deal with the subject matter broadly and thoroughly, and perhaps deeply. Certainly a paper that's really, really, really narrow is not, I mean, of course, when we use the words narrow and broad, we're referring to the particular field that we're talking about. I mean, there are very few people who write a paper as broad as relativity paper, okay? I mean, no, there aren't many Einsteins, but there are lots of classic papers, but they're classic within their field. So within their field, they really cover some topic thoroughly, broadly, and they do it relatively deeply. I think all of these are attributes, not necessarily essential attributes, but in general, classic papers have characteristics like this. Okay? I'm going to guarantee you that 90% of the papers that you read are not worth remembering. There's a very famous science fiction writer, Ray Bradbury, who said that, as in everything else, 90% of science fiction is garbage. And I'm afraid that's true in general. And you don't want to clutter your mind up with garbage. One thing you have to learn to read, do early in your careers, is how to read a paper. You have to learn to read a paper. Okay, anybody here not read a scientific paper yet? Good, okay. What's the first thing you read when you read a paper?
The abstract?
Hmm?
The abstract?
Oh no, there's something before that.
The title.
The title. If the title is irrelevant to your interests, you're not going to read it. Second thing, I wonder what that could be.
Abstract?
Abstract. What's the third thing you should read?
Conclusion.
Conclusions. Don't look at the stuff in the middle. Okay? What do you think is I mean, that's pretty logical, I think. Title, abstract, conclusions. If you don't learn anything by doing that, you're not going to read the paper. But suppose that you read the abstract, you read the conclusions. By the way, that's why I really like always to write a summary or a conclusion section in the papers that I write, because I think it's a gift to the reader, even though by the time you're writing the conclusions, you're sick and tired of that piece of work, and you just want to send it in. But it really helps the reader direct them to your work. After that, and suppose you're interested in the paper, what do? What do you read?
Diagrams.
Hmm?
Diagrams.
Very good, very good. The figures really tell the story. And you know, if you can just go through the figures, then you decide, yeah, I really want to dig into this paper, and I really want to burn through the equations and really understand the experimental methodology. But don't waste your time reading the details of the experimental methodology if the figures don't tell you anything. And I dare say that you could spend no more than 5 minutes on a paper and say, less than that sometimes. But you don't want to spend hours reading papers that are no good to you. You just don't have enough time. Okay? And what you're really hunting for are these kinds of classic papers. And my own advice is when you're digging into something new that you don't really know that much about, what you want to find are not the individual papers. You want to find a good review article. A good review article is worth 100 papers. And the tracking systems, like SciFinder and so on, they let you narrow your search to review articles, so you're not reading everything in general. It's worth that when you're just digging into a field at the very beginning. Sooner or later, you got to read the real papers, but reviews can give you a lot of information really, really quickly. And sometimes authors who've written a lot of papers wind up writing the reviews, and they do a better job of summarizing their viewpoints in the review articles rather than in the primary literature. Reviews are not primary, they're secondary sources. Okay? But they're just as authoritative as the primary papers. Okay, so let's get back to the course now, if you don't mind. Okay, here are some problems I want you to do. The answers to 1, 6, 8, 9 are going to be posted. By posted, I mean I'm going to put the answers in the folder for the course. But work on all those problems at the end of the first set of notes, but especially 1, 6, 8, and 9, because I'll give you the answers. Second, I want to give you a little extra problem to work here. I want you to compute by means of the summation equations the first and second central moment for the Craig machine when k prime is 1 and the number of transfers r is 5. So I want you to look up those numbers in my slides. They're given in the slides. For that case of r equals 5. I want you to compute the summation to calculate the center of gravity and use the summation to calculate the second moment about the mean. And then I want you to use the equations that we generated for the first moment, which is the first moment is equal to r times q, and the second central moment is r times p times q. So you're going to compute each of those numbers in 2 different ways. They better agree. If they don't agree, you don't know what you're doing. Okay, so it's an internal check. But you need to know how to use those formulas. And last, there will be a quiz on Wednesday. Okay, it'll be short. It'll be 10 minutes. But we've certainly gotten far enough for there to be lots of stuff to ask questions about. Okay, today we're going to go deeper, and we're going to get into where the Gaussian peak shape equation comes from. We're going to get into a second way of using the Craig apparatus, and that's for what we call a continuous Craig apparatus, which is a little bit closer to chromatography than the discontinuous Craig apparatus. Then we're going to talk about 3 different ways that we develop a chromatogram. The process of getting a chromatogram is called development. We're going to talk about the zonal chromatogram, and this is where we just add sample to the very first tube, only once, to the 0th tube. And then we keep adding fresh eluent. This is what's called zonal development. If we keep replenishing the sample into the first tube, into the 0th tube, so that every cycle we add more, that's what's called frontal development. And then there's a third way of developing a chromatogram, which is called displacement development, which you have to see the picture in order to understand it, so I'm not going to tell you exactly what that is. And then we're going to talk about what happens when you're doing a separation, some sort of partitioning operation, or adsorption operation, or whatever, and there are chemical processes taking place in parallel with the separation. And there are many, many, many forms of this. One of them is when, for instance, you're separating, say, weak acids and weak bases, and these acids and bases are undergoing ionization during the process of separating them. This is especially important when you have an aqueous mobile phase, because lots and lots of things ionize in water. It's especially important in biological separations because the vast majority of the compounds that you're separating in biological operations have functional groups which can be protonated, which can ionize, so on and so forth. So we need to understand that. Okay, so on, what was it, Friday, I gave this general equation for the fraction of the material in a given tube N after so many transfers R if the retention factor for the sample was K prime. And this is the generalized binomial expansion result. And what we found is that the first moment, which means the tube in which the center of mass of the sample is found, we call that center of mass N bar, that's the average tube number, will be equal to R, the number of transfers, times Q, which is the fraction of the sample that's in the mobile phase in all of these identical tubes. And the variance of this distribution, I'm sorry, I'm jumping ahead of myself. So, given this equation M1 equals R times Q, we can now solve a very, very important question. I want to know how many transfers I have to do, in other words, what is R, so that the center of gravity of the distribution has moved to the last tube. That's tube N. So basically, we take the equation M1 equals R times Q. We set M1 equal to the nth tube. And we then invert the equation and we calculate that R is equal to big N, the number of tubes, divided by Q, the fraction in the mobile phase. Now we can easily, we know that the fraction Q that's in the mobile phase is 1 over 1 plus K prime. So therefore, the number of transfers that you need to do to get the stuff to the last tube is the last tube's number, N, times 1 plus K prime. The total volume of eluent needed to go into the 0th tube to push the center of gravity from the 0th tube to the last tube, the total volume of eluent will be equal to R, the number of transfers required to do that, times VU. VU is the volume of fluid in the upper phase, that is, the mobile phase. So plugging that all together, VR, which is also called the retention volume, is equal to the volume of mobile phase in the upper part of the tube times N, the total number of tubes, times 1 plus K prime. And I can put that all together, and that gives me VR, the total volume of eluent, equal to Vm, which is the total volume of mobile phase in all of the tubes. So it's N times VU, VU being the volume of eluent in one tube, N being the total number of tubes. Big Vm is the total volume of mobile phase in the whole Craig apparatus, times 1 plus K prime. And that works out to be Vm plus K times Vs, where Vs is the total volume of stationary phase in all of the tubes. This last equation is really an important equation. It tells us when we expect the stuff to come out of the column. At what volume of eluent will it come out of the column? This is called the retention equation. And it's really the most important prediction that the plate model makes. Now I want to goof around with the plate model equation a little bit more. I'm going to take the limit as the number of transfers becomes really large. And just like with the case of repeated extractions, when we took the limit of an infinite number of repeated extractions, a discontinuous equation became a continuous equation. The same thing happens with the equation for the mole fraction in a given tube. It goes from being a discontinuous equation to a continuous equation. And we find out that it looks like a Gauss function. And the result is the fraction of the solute in any given tube is equal to 1 over root 2 pi, 1 over sigma n, where sigma is the standard deviation of the peak, exponential minus n bar squared. So the exponential minus something squared defines a Gaussian function. And then, of course, there's a 2 sigma squared in the denominator of the argument of the exponential function. So this is what happens to the peak shape when you plot it against tube numbers after you've done a large number of transfers. We can also show fairly easily that the peak shape function, the function as the number of the tube number, can also be written as the function of the fraction of the solute in the last tube, the fraction of the solute in the last tube as a function of the volume of eluent that has gone into the zeroth tube. And this is the volume of eluent that you put into the column. VR is the predicted retention volume from the plate model. And sigma v is the standard deviation of what that peak looks like. It's fairly easy to calculate that standard deviation. And it's simply equal to VR over root n, big N, the total number of tubes in the system. So if you know the retention volume, and you know how many plates or tubes you're dealing with, you can calculate the standard deviation of the peak. And so you can plug the sigma v into the equation, and if we want the actual concentration instead of the mole fraction, we simply take this equation and multiply it by the massive sample that was injected at the beginning of the experiment into the zeroth tube. So W is simply the mass in any units you want. It could be in moles of A, it could be in grams of A, I suppose it could be in pounds or ounces of A. Don't know what other units one would care to use. Now milligrams, I suppose, or millimoles, or micromoles, or whatnots. So this is an exceedingly important equation because it tells us what the peak is going to look like at the end of the set of tubes as we push mobile phase into the upstream end of the column. If we use this equation and replace the sigma v here and here with that equation, we get another useful equation. The concentration is a function of volume, and the plate number, the number of theoretical plates, the number of tubes in the Craig machine, whatever you want to call it. And we're going to investigate the properties of this equation in some detail towards the end of this lecture. So this is also a very important outcome of using the plate model. It only works when R is large. It turns out that the real condition for this equation to work is that R times P times Q is greater than about 30. If this is so, if R times P times Q is greater than about 30, the deviations between this final equation and this equation are going to be virtually invisible. I mean, that you're not going to be able to detect them by eyeball. Okay, now, the Craig apparatus that we've been talking about, and the one that I showed you when I showed you some pictures, is a discontinuously operating system. You have to equilibrate each tube and do the transfers. You have to stop the equilibration, do the transfers, and then repeat that discontinuous set of processes. You have to do that a lot. But there's a continuous way to do the Craig apparatus, and that is to somehow build into each tube a really effective mixing device, a stirring rod, a magnetic stirring paddle, whatever you want to call it. And instead of just adding the fluid to the zeroth tube and replacing all of the fluid on each cycle, you continuously flow in mobile phase. And people have built these kinds of apparati. So what I'm telling you is that the transfer process, R, now becomes a continuous variable. Not, R is no longer equal to 1, 2, 3, 4, 5, but it can be equal to 0.01, 0.011, 0.012, 0.013, 1, 1.1, 2, 2.67. It's just a continuous variable representing the amount of material that has gone into the very first tube. And then that, of course, moves over into the second tube and into the third tube. Now, it may be hard to believe that this system will ever work at equilibrium, and I agree with you. It's hard to imagine that you could mix so quickly that it would be at equilibrium. But if we assume equilibrium, then we can calculate the amount of material in each tube as a function of the continuous variable. And the solution to that problem is this equation, where x is the fraction in a given phase, n is the tube number. The tube number is still discontinuous. It's 0, 1, 2, 3, 4, 5. R is a continuous variable representing the amount of material that's gone into the first tube, and it's actually the ratio of the volume of eluent relative to the volume of eluent that fits in one cell. So R is continuous, N is discontinuous, and we wind up with this function. So then we can plot what the peak shape looks like. If we have a system consisting of one cell, or two cells in series, or three cells in series, or four cells in series, or N, you could do this for 100 cells in series if you wanted to. It's actually possible to calculate it out to any number of cells you want. You'll notice with N equal to 1, this case right here, it rises very sharply and then it comes down rather slowly, so it's pretty asymmetrical. But as N increases and we have more and more cells, it's becoming more symmetric. And guess what the limit is when you have a large number of cells? It's Gaussian function. So this is another way that you can get at the Gaussian function. Both the discontinuous and the continuous Craig apparatus predict a Gaussian peak in the last cell. But you have to have a fairly large number of cells in series for it to look like it's really Gaussian. Okay. Now I'm changing gears at this point. You can still imagine that we're using the Craig apparatus, or you can imagine that we have a real chromatographic column, be it GC or LC or ion exchange or whatever. And we're going to look at the different ways in which we can develop a chromatogram. The first and the one that's most familiar to you guys, I'm sure, is called elution development. And you're going to get a chromatogram that looks something like this, where this is compound 1 that's relatively unretained, compound 2, which is somewhat more retained, and compound 3, which is still more retained. So what I'm telling you is the K prime of this species is less than the K prime of this species, which is less than the K prime of that species. We're putting the solute, the solute mixture of 1, 2, and 3 into the system one time and one time only at the very beginning of the chromatogram. And what you'll see then are these separated, what you hope to see is these separated Gaussian peaks. So this is called elution development. It's also called zonal development. Because these peaks come out, or hopefully come out, as individual separated zones. It's possible to do the chromatography in another way. What you could do is you could take your mixture of 1, 2, and 3, put it in your mobile phase, and continuously pump that mixture into the column. And never turn off the mixture. Just keep pumping it in, keep pumping it in, keep pumping it in. You're no longer doing elution or zonal development. You're doing what we call frontal development. And your chromatogram is going to look quite different. It's actually the integral of this curve. So if you were to literally integrate that, you get a curve that looks like this. Now, let's start at the beginning, where you first start pumping the stuff in. Nothing can come out because the material has to propagate through the entire column before you can start seeing anything in the last tube. So it starts at 0, you get nothing until the solute, which is least retained, starts to come out. And it doesn't all come out at once. It's going to curve up and then roll over and approach a plateau. And the plateau happens, and this is very important, the plateau happens when the entire system has reached steady state, so that the solute concentration in the mobile phase in the first column and in the last column are the same. That's when you get to a plateau. And if you then add a little bit more solute, of course, the concentration at the exit can't go anywhere. It's got to stay the same. The system's in steady state. Now, if compounds 1 and 2 are really separated as well as I've shown up here, then you'll stay on the plateau for compound 1 for a while until compound 2 breaks through. It'll curve up, come up to a plateau. Now, in the plateau region here, the concentration of compound 2 that you're putting in is equal to that in every single tube, and it's equal to that which comes out at the end of the column. So it's steady state again, it's another plateau. And then finally, if the separation between 2 and 3 is really good, you will get a third breakthrough. It'll come up, it'll go flat, and at this point, the entire system, every single tube is filled, has got the same concentration of compound 3 as in the first tube, and it's just equal to that in the last tube, and it's equal to that which comes out. But you can see that there's a huge difference between frontal development and zonal development. In zonal development, I can capture this peak, and it's pure, or 99.999% pure. It's not 100% pure. Otherwise, what I told you the other day was not true. This is virtually pure, and this is virtually pure. When you do frontal development, the only compound that you can get out that's virtually pure is compound 1. And you have to stop collecting it before breakthrough of compound 2. Because what's coming out in this plateau is a mixture of 1 and 2. And what comes out after this plateau is a mixture of 1, 2, and 3. So there's really no point in running frontal development until you see 2 and 3. I just want you to understand what's going on, which is why I showed the 3-component mixture. But this is really the only one that you can purify. And the virtue of this technique is that you can get a lot more purified 1 this way than you can that way. So this is actually used for purification of, a scale-up kind of purification. Frontal development is also very useful for understanding the details of what's going on in terms of the equilibria inside the column. And we may get back to this issue later on, but for instance, one thing it can do for you is tell you what is the total capacity of this column for handling sample. Elution development doesn't readily tell you that. Elution development is great for analysis. It's great for learning about peak shapes and stuff like that, but it really doesn't tell you much about how much sample can you really load on the column. The third kind of development that's really very popular among the prep scale people, and remember I said I wasn't going to talk about prep scale very much, and this is probably the only time I'm going to mention displacement development in this semester. But if you ever have to do prep scale work, this is the way to do it. Frontal is okay because it can get you pure A, but it can't get you pure A, B, and C, or 1, 2, and 3. Displacement theoretically can get you pure 1, pure 2, pure 3 if you have a 4-component mixture or an n-component mixture. In principle, it can get you each of those components in a purified state. What you do in displacement development is first you load onto the sample, onto the column, a lot of 1, 2, and 3 in one shot. Okay, so you load it on a lot of it in one shot. Then you add to your eluent some compound, which we're going to call a displacer, which actually binds to the stationary phase more tightly than anything in your sample. Okay? And you keep pumping in this displacer. Now, compound 1 is less retained than 2 or 3. 2 is less retained than 3. And the displacer is more strongly retained than anything you put in the sample. It binds to the stationary phase more tightly. So what happens when you pump in displacer continuously is the displacer jams compound 3 out of the first tube. Compound 3 displaces compound 2. Compound 2 displaces compound 1. And then they all come out like a series of boxcars, if you will, in a railroad train. All the 1 comes out, all the 2 comes out, all the 3 comes out. The height of the steps up and down, is proportional to the amount of 1, 2, 3, 4. The width of the zones, the width of the 1, 2, 3 zones are all pretty much the same. Depends on the number of theoretical plates, the big N, the number of tubes in the apparatus, the number of theoretical plates in the chromatogram. But the height is related to how much of this stuff has been loaded at the beginning of the chromatogram. Now, you can actually load a lot of 1, 2, and 3 this way, and you're making use of the entire column all the time. So that's why displacement chromatography is used a lot for prep scale work. You can purify more than one thing, and you make very effective use of the entire column when you do the operation this way. So these are the 3 ways that we generally do chromatography. In all honesty, an analytical person only cares about this. But I don't want you to go around saying you heard nothing about preparative scale chromatography. You heard 5 minutes of it. Now, I'll take another 2 or 3 minutes and talk about chemical effects in chromatography. Suppose we have some compound HA that is a weak acid. And suppose we use our Craig machine or a chromatogram, like a real column, and we have a mobile phase which is primarily water, and a stationary phase which is some kind of non-polar organic, something like hexane or diethyl ether or carbon tetrachloride, something that's not very soluble in water, so we can keep the two phases separate. HA could be something like benzoic acid, just for simplicity's sake. At a low pH, you expect the benzoic acid will be completely protonated. It will be COOH form. That form is actually much, much less soluble in water than is the ionized benzoic acid, the COO minus form. So as you change the pH, and you raise the pH from an acidic level to a basic level, the benzoic acid becomes benzoate. The benzoate is much more soluble in water than is the benzoic acid. The K prime factor is going to go down. It's going to vary a lot with pH. If we had two acids that had identical chromatographic properties, by that I mean they had the same K factor in the system, but the two acids have different pKa's, you could separate them if you use the right pH range. Ideally, you would want to work at a pH where one of those acids is fully ionized and the other is not ionized at all, and you get a beautiful separation. But that would require a difference in pKa's of about 4 units. As long as you have some difference in pKa, you will be able to find a pH where you can do a separation. It may not be a great separation, or it could be a very, very good separation. It depends on all the conditions. So the point of this is that when you have chemistry going on, it can interact with the chromatography to either make your separation life harder or easier. If you pick the wrong pH, it'll make it harder. There's lots of other chemistry that we can build into the separation if we can do so deliberately. If we were separating metals, we could possibly add some ligand that differentially binds the metals. In biological separations, people do all sorts of things. And they use antigen-antibody binding processes, enzyme substrate binding processes. There's a whole slew of biological binding processes. Sometimes molecules will actually dimerize, and that can have a big impact on their chromatography. For instance, acetic acid in a nonpolar solvent like hexane or carbon tetrachloride or diethyl ether, it loves to dimerize because it inherently contains a very good hydrogen bond acceptor and a very good hydrogen bond donor. So it can form these little cyclic arrangements where they've satisfied their hydrogen bonding interactions. It's a very common thing in reverse phase chromatography to deliberately form an ion pair. If you have some compound like an amine, primary amine that's protonated, and you want to get it to go into a nonpolar stationary phase, it's not uncommon to deliberately add to your mobile phase a species with the opposite charge, which can form an ion pair with your analyte. Chemistry which may seem exotic, for instance, charge transfer complexation, is used all the time for separating, for instance, molecules that have double bonds in them. Silver ion is a very, very, very highly polarizable ion, and it loves to form charge transfer complexes with virtually any compound that has pi bonds. So be it gas chromatography or liquid chromatography, people will impregnate the stationary phase with silver or mercury or maybe even cadmium, all of which like to form complexes with double bonds. The point is that these complexes are usually very selective, and so you can greatly improve your chromatography. And I could go on for hours about this, but I'm just going to say et cetera, et cetera, et cetera. There's a huge amount of chemistry that people use in separation science to help them out when the system's not good enough to do a good separation without the chemistry. So this stuff is, especially in biochemistry, is very heavily used. Okay, sorry for going over, but we're done with the first section. On to Gaussian peaks on Wednesday.